Okay, so now that you've learned about the electromagnetic spectrum and all of how the electromagnetic spectrum works, what all is a part of it, what all falls on it, all of the electromagnetic radiation you see, now you're going to need to learn about these two formulas that you actually apply the knowledge you've learned and apply the concept that you've got from it. Make for sure and watch and be careful in every step you make in here, because in every area it's easy for you to make a mistake and for it to just wreck you. So please, at all costs, be careful. And during this video, press pause, take notes. You can play this video over as many times as you want. Do whatever you feel that you need to until you get the understanding of what I'm discussing here. If you have questions, come see me. I'll answer all your questions whenever we get back to school, and we can work on it then. Whenever we come back to class after this video, we're going to work on these problems and work on using these formulas. So it's crucial that you understand what I'm talking about. So the first equation we're going to talk about is the top one here. As you can see here, it's C equals lambda times nu. Okay, the funny looking H thing, that's lambda. The funny looking U, V thing, that's nu. Okay, all these are Greek letters for representations of information we find on the electromagnetic spectrum. So for here, this is the speed of light. The speed of light, you all are probably familiar from hearing Albert Einstein's famous equation of energy equals mass times the speed of light constant squared. What I want you to make for sure you remember is it's a constant. Don't forget it. And make for sure that you remember the constant. The constant will be 2.98 times 10 to the 8th meters per second. Make for sure you got the units for the speed of light constant is meters per second. Alright? Lambda is wavelength. So when lambda is our wavelength, and nu is our frequency. Okay? That's all that is for that first equation. Make for sure you got the constant. Make for sure you know which each part of these are symbolizing. Then the second one is down here at the bottom. Energy, which is symbolized by E, so E is for energy, equals Planck's constant. The regular lowercase h is for Planck's constant, and it is, dun-da-da-da, you got it. It's a constant. So make for sure you remember it's a constant, and make for sure you remember the number. It's 6.626 times 10 to the negative 34th power. And make for sure to get the units right. The units is joules times second. Okay? Joules times seconds. It's not joules per second, it's joules times second. So make for sure you get that. And then the last part of this equation is just nu. It's frequency. Okay? This allows us to incorporate these two equations together, to work them together. So frequency is your key. And you can use frequency to rewrite these equations to where they link together. So if you take the speed of light equals lambda times nu, and we have the second one, energy equals Planck's constant times nu, then you'll find that these two can just be rewritten and substitute in for the other one. So I'm going to rework this one to where we can fit it into the top equation. So for example, they're being multiplied. Planck's constant and nu is being multiplied. I'll divide by Planck's constant, and I'll find that frequency is equal to energy divided by Planck's constant. Now I can substitute this in to this equation up top, and you will find that the speed of light equals lambda, and then substituting in for frequency, this what we got down here, energy divided by Planck's constant. They link together, and it's important that you remember that they're linking together because you can deal with problems that you'll have to be able to do this. You can either do it as a two-step problem, or you can do what I've done here and put the equations together. So an example of what that would look like problem-wise, I have written at the top of the board. So the question reads, what is the wavelength for a photon of light that has energy of 3.62 times 10 to the negative 19th joules? Do what I've done with you guys so far. Write down what you're looking for. What are you trying to find? You're trying to find wavelength. So lambda. What's an equation you can use that you know to find lambda? You know one now. You can use the speed of light equation. So you know you can use the speed of light equals lambda times nu. So speed of light equals wavelength times frequency. If you want to, go on and readjust this. Do some algebra and get it to where lambda is by itself. And you find lambda is equal to the speed of light
the following statements independent of the office
divided by frequency. Okay? So this is the new equation I'm trying to work with now. I'm trying to find my wavelength. I know the speed of light. I need a frequency. If you get to this point and you cannot find an answer, that's when you know you got to use the second equation. You're going to have to use energy equals Planck's constant times frequency. You're trying to find frequency, so go on and work this around to where it'll fit better for you. So we'll do algebra like we did before and find that frequency is equal to energy divided by Planck's constant. And go on and substitute those numbers in. So go on and substitute in for energy the 3.62 times 10 to the negative 19th joules divided by Planck's constant, which is 6.626 times 10 to the negative 34 joules seconds. This is good because joules will cancel and it'll leave you with seconds on the bottom. This is a great time to make for sure that you understand. When we're looking at a frequency, frequencies are measured in hertz. But hertz are equal to inverse seconds, so 1 over second. It's also equal to seconds to the negative first power. So this is good. Seconds are in my denominator, which means I end with the units I'm looking for. You want that to happen. So work that out. Punch it into a calculator. And you'll find frequency. You'll find the frequency to be 5.4633 times 10 to the 14th hertz. I know it's hertz because I'm left with seconds in the denominator. Now I have this new piece of information. Now this new piece of information can be used to plug into this equation and find my answer. So let's plug it in. So we're going to find a wavelength equal speed of light divided by frequency. Speed of light is a constant. You already know it to be 2.98 times 10 to the 8 meters per second. And we're going to divide that by guessed it, 5.4633 times 10 to the 14 hertz, which is inverse seconds, which will mean seconds will cancel, leaving me with meters on the top, which is what I want because wavelength is a measurement of length. So meters is a good base unit for a measurement of length. So we're ending with our units good. Now, just keep working down and you'll find, give me a second, punch it in the calculator. 2.98 second e to the 8 divided by. You'll find your answer to be 5.456 times 10 to the -7th meters. Okay? Now you can readjust this if you want. You can do metric conversions if you feel better with wanting to put this in nanometers. I've already covered that, so I'm not going to cover that any farther here. But you can adjust this, but this is a correct answer. So 5.456 times 10 to the -7th meters. We just found the wavelength for a photon of light given its energy. This is about as hard as the questions can get.